Okay, I think that we can start now. Well, hello everyone. I'm going to talk about hardening sentiment, adversarial thinking in action. So this presentation, the idea is to give you an overview of the latest 8 months and the review process that have been going in the libsecp library, the main PR, for silent payments. That's the cryptographic primitives. So first, to let you know why I'm talking about this, I am Nymius. I'm a grantee funded by BTK Foundation to work on silent payments in BTK library. I also am an alumni from bitcoindev 2024. So the work that I'm going to present here is the effort of multiple contributors, Joseph A. Ruben Thompson, the Stack, Jonas Nick, and a lot of them. So this is not particularly my work. I'm just presenting it here to let you know. Well, first of all, who has any idea of what silent payments are? Okay, I'm just going to give a quick overview. So silent payments is a way to share static code, and by doing that, you don't have to resend a new address to your sender each time that you want to receive Bitcoin. So it's a very good way to avoid the address use without having to care if you are, without communicating each time with the sender. So here, I'm going to present first the main case of analysis for silent payments, where we were 8 months ago. So for sending and receiving, you need 2 processes. So first, you have the action that you must perform in the sending side, but the most expensive and most computing intensive task is on the receiver side. So you have to perform a scanning task that to allow a good user experience should be between the usual expected time boundaries that you need for an application for users. So it's critical to have a broader adoption to have a nice user experience, and so that's we are focusing so much on this kind of process. The first proposed algorithm was something like this. So for silent payment scanning, you have to go through all the outputs in the transaction, do some cryptographic computation on the transaction itself, use that to derive the possible script key that you can obtain from that information, and then check with all the outputs. So that requires going through all the outputs, doing this computation. The main critical points in this computation is on the cryptographic operations. So elliptical cryptographic operations are costly. Some more than others, but here are the main ones. So first, you have to derive the public key that can go inside the pay-to-tablet script key, and then you do some subtractions here to get two other possible ways to get the silent payment. And well, those are mainly the operations that we are counting in to get the complexity or the number of iterations of this algorithm. So this was the first proposed algorithm. We were going through all the possible derivations that we had, and then we were checking all the outputs to find these possible silent payment outputs. So, as we can see here, we have 2 loops, and that gives you a rough idea of what what's the number of operations that this algorithm is computing. So roughly that's k times n. If we say that, well, the first loop goes through k iterations and the second one goes through the number of outputs, that's n. So for this algorithm, we have different cases. So we have to analyze that it's not just like this. It's not just we are going to go through k times n operations, loops. So we must analyze in a base per base cases. So first of all, let's say that we have an array of n elements. That's our vector of outputs in a transaction. So what we want to do with this algorithm is derive the possible silent payment output that we are trying to find, and then check with each of the outputs in the array if that output belongs to us or not. Let's start with 3 elements. So here the number of derivable silent payment outputs is less than the total number of outputs that we have in our transaction. And let's say that those are ordered. So we have ordered silent payment outputs back at the beginning of the transaction. In that case, the first check that you do is going to give you is going to be a positive one. So you have a match. So after having that match, you can break the loop and add that to your found outputs. Then we have to check again to see if we have another silent payment output inside the transaction. If we keep doing this as the outputs are ordered, we are going to find them very easily. So we repeat that for the first output, second output, third output, and it's very easy to find it until we reach the point that we don't find any more outputs. And here, instead of finishing here, what we should do is continue until the end to see if there is any other output related to the first one. So this process takes to compute the second output, we must have find the first output. So they are dependent. So we can find the third one if we haven't find the second one. So in this process, we have to go through all the way to see if there is this possible fourth output in the rest of the output of the vector of output. So this gives us roughly a case where upon 2 number of iterations, the calculus is more complex than that number, but roughly that's the idea. And if we have a vector of outputs with a lot of silent payment outputs, we end up with something closer to n squared. So we have almost as many silent payment outputs as the outputs that we cover in our vector. So if we have much less silent payment outputs than the number of outputs in the vector, then we are closer to this number of iterations. What happens if the silent payment outputs are marked at the end of the vector of outputs? Well, as I'm raising them here, we have the outputs at the end. They are also ordered, but in reverse. So we have to go through all the outputs till the end to check that we have a match. The same with the second one, we have to go through all the way until we find that we have a match. Same with the third one. And we have to repeat this another time to check that we don't have a fourth output. So in the usual case, this is our number of iterations, case time n. Again, if we have a lot of silent payment outputs, we are going to have to repeat this, and this is closer to n squared. So we are not. It's a little bit worse than the case where we have all the outputs at the beginning. And if we have very few silent payment outputs, then it's closer to the usual case, so k times n. What's the difference between both cases? Well, usually it depends, but as if k, the number of silent payment outputs is much less than the number of total outputs in the transaction, then this is the difference between both cases. But as we get closer to the maximum number of outputs, then we are going to have something this is not going to occur to have so much weight in the computation. So as k is closer to n, then this goes to 0 and it doesn't matter. But what happens if the outputs are evenly? Yeah.
Sorry, so with k is the number of silent payment outputs, and n is the number of outputs?
Sorry. The k is the number of silent payment outputs, and n is the total number of outputs in the transaction. So what I was going to show now is what happens if those are evenly distributed in the vector of outputs. So this could be the case. We have we don't have all them back at the end or the beginning. They are evenly distributed, still order, but well, yeah, it doesn't matter the order. So it's like we can have to scan 2 times to find the first one, then another time to find the second one, and then we have to we go back to the first one at the beginning. So that's what we do. Actually, the order here is wrong, but let's suppose that we have to first find the first one that was here, then we should find the second one, and then we find the third one. So the order here is wrong, but the idea is that you keep doing these iterations until you find them all, and you know for sure that you won't have any fourth silent payment output in the transaction. So the complexity or the number of iterations of this is around n times k upon 2. So it's like you have some improvement there. In the worst case, where you're closer to k is closer to n, you have you are also reducing the complexity of the number of iterations by half. The same happens. The same is true for the case where k is very low or far from n. So what are the issues with this? I have shown you that the complexity is around the n times k number of iterations. It's not something as good as we would like, but we cannot. There is no way to go through this number of iterations by adjusting the algorithm. Simple. So let me talk about the worst case. Here we are as I mentioned at the beginning, I was referring as the benchmark operations as the elliptical operations that we have to do. So the worst case is the one that maximizes the number of elliptical operations that we have to perform in a single block. In another adversarial case, that block is one that sells a lot of transactions that fills all the block with one-to-one transactions, and all of them creating a silent payment output. So every receiver is going to have to scan for these silent payment outputs. So it's going to have to compute at least one elliptical operation. That could be transformed in an adversarial case in a single transaction filling a block with just a silent payment output. So that maximizes the effort for a single user. That is something that we don't consider that as the worst case as that, because you have to come up with the case that you want to create a transaction that is filling a block, you have to pay the fee, so it's something that is more convoluted to do.
Can you clarify why a single transaction filling a block is worse than?
If like a single transaction had 5,000 or so silent payment outputs for one user, it affects one user.
Yeah, exactly. As I said, you cannot compute the second. To find the second output, you have to compute you have to find the first silent payment output, and you're repeating that operation for each one of the outputs that you have in the transaction. So if you're creating a single transaction free in the block, you have to go through around 23,000 times the number of operations for a single silent payment output. But that's just for a single user. So I'm going to comment later about what are the improvements that we find for user that doesn't have matches here.
Yeah, I have a question on if you've done any benchmarking on what is the runtime? Like, what is the because I've heard a lot about like silent payment scanning is like very expensive. But what exactly would be the runtime if there was a block full of, let's say for the one user, there was a block for one user, and so they had to do all these elliptic curve operations. What would be like the runtime for processing that block for one user? Do you know?
Yes, we have the benchmarks in a few slides, so we can still there. Yeah.
So when you say a single user, that means that I have a silent payment address, but if I see one transaction in the block, can I know that it doesn't pertain to me, or do I have to?
Yeah, I just by looking at the transaction without doing any elliptical operation, I cannot know that that transaction is for me. So I have to go through all the transactions in the block if they are selectable for silent payment outputs. Okay. Any more questions? Okay. As I said, the first case, we call them that the worst case, and the second one is the target attack, because of the differences between adversarial and not adversarial. So the target attack, well, here, as I was saying, you need around 23,000 silent payment outputs to create this attack. So for that, you have to send this amount to the same receiver to slow it significantly. And like we were trying to find the rationales behind this kind of attack. So the best that we could do is, well, if you repeat that enough times, then you are going to increase the delay that receiver is experiencing scanning silent payments. And this can be as low as $250 USD in fees. So, like right now, if you go to the mempool and we see the total amount of fees that blocks are paying, blocks are receiving in terms of fees, maybe that's around, I don't know, $8,000. But from time to time, the mempool is empty enough to allow this kind of fees, so that can be performed for not as much money as we think. Again, we haven't found any rationale for that, but we could be thinking in motivated enough attackers that would like to do that for a single user. So after defining these cases. During the review process, the contributors and reviewers started to come up with different optimizations. So the first one that came up after the case for the target attack was the label set algorithm. So it was proposed by Vox. The idea is that you can sort first the transaction outputs to make them easily searchable with binary search, and to compute early the possible script keys that you may find for your labels. So this is assuming that you don't have as many labels. It is a case that is optimal in that case. But so we are going to find later what are the cases where this algorithm doesn't perform that well. So here again, I'm highlighting the elliptical operations. The heaviest one is the multiplication, so it's happening here. And once we have the derivation, we can go through all the labels, derive them, and compute and go to find them in this sorted array. So here we have the number of derived silent payment outputs, that is k, the total number of outputs is n, and the total number of labels is l. So the number of iterations of this algorithm is around k times L times the logarithm of n, the logarithm of the number of outputs. But as you can see, as L grows, it can get worse very fast. So it's only efficient if the number of labels keeps low. There is another optimization that is to remove the number of found outputs. That's something that well, I assume that everyone would like to do that, to not check twice the same output. So if you start removing the outputs that you have already scanned, and you have checked that it's a silent payment output that belongs to you, and you remove it, the total number of iterations in the normal case is around the size of the silent payment outputs open 4. And then if you have much less silent payment outputs than the size of your vector of outputs, then it's k times n, the half of it. And if you get closer to the number of outputs, that would be like worse. That you have to scan and compute more operations for all your silent payment outputs, and that has a good improvement by around half with the worst case of the other operations. Remember that. I think that in the best case we have a n squared about 2, and here we are above 4, so it's like 50% improvement. Another thing that was discussed is this idea of, well, if the performance of the algorithm depends on where the outputs, the silent payment outputs are packed, then we are getting a very a lot of variance in the scanning. So from time to time you get a good performance or good enough, and then if you go through the all the silent payment outputs packet at the end, then your performance gets worse. So to get a scanning without that much variance, what you could do is randomize the outputs. So you have good chances to make them evenly distributed in the array, and then that variance is not that high. So here I'm mentioning that, well, we have seen that the performance changed from the order of the outputs. And one third thing that is more related to elliptic curve cryptography is batch inversion. So in elliptic curve cryptography, the inversions are much more expensive than multiplications. So there is one trick called Montgomery's trick, and that allows to change from n inversions to 1 inversion and 3 times n-1 multiplications. And that also improves the case for people for users that are not receiving silent payment outputs in that transaction. So the no match case gets at 2 times, around 2 times or between 2 and 3 times improvement. And another thing that was discussed after going through these optimizations and trying to find a good spot where we wanted to stop optimizing is the limitation of the number of silent payment outputs that you could add to your transaction. So that's a breaking change in the specification. And the idea is that it doesn't remove the original problem, but it bounds the problem to an acceptable state. The discussed number range from 100 to 1,000, but also 2,350. That's the number of, that's the limit of output that you could get by the standard rules, I think. So that's why that number was less. So going through the benchmarks, this benchmark table was produced by Ruben Thompson. It was updated recently. The idea here is that you have each column is a different scenario, and what this table is counting is the number of elliptic curve operations. So here is roughly the number of operations that got performed. You have to perform for each one of the transactions, each one of the outputs, and that's why you are computing the product. And the base case is the worst case, that is the one sending a full block with all one-to-one transactions. Yeah.
Is that saying 1,348,000 elliptic curve multiplications in like the worst case? In the max transaction number?
Yeah.
1 million? Oh my god. Yeah, I mean that takes a long time.
Here, yeah. Yeah,
no, because I've done like some stuff that would be like 50,000 elliptic curve multiplications per block, but 1 million. Now I see why like it's such a big thing to optimize, because in that case it's really bad.
Yes.
I mean, I imagine that's like minutes to verify the block.
Well, at the beginning with the baseline algorithm without optimization, it was. I think that the worst that I have run the benchmark was like for 10 minutes.
10 minutes to verify.
Yeah.
And probably on good hardware as well.
Yeah.
It was 10 minutes. Yeah.
So this was what, right? Because we want to have a broader adoption, and we cannot get that if we have a bad user experience. So here we can see that the label set, how was the behavior of the label set against the base case. Here we can see that we have a 6% improvement in the base case, but then as we are adding more labels and more labels, it was worse fast. And here is the worst target case. So we have this number of outputs, we have a single transaction, and we have just 2 labels. And well, the label set case is very performant, but we cannot have as many labels as we would like. So that's something that we discussed, and we were not interested in having a case where we cannot derive at least a good number of labels. So this is also a benchmark table produced by Robin Thompson, and the idea is that here we are looking just at the worst case, at the target case, and we are the table here is showing the different performance in the different limit k cases. So here we have 100, 1,000, and the limit of the standard rules. And these are roughly the numbers that we are getting from that. So we have first the one that is not limit, and the second one is the one that is limit. So we can see that still we have 37 times worse performance for the case with the output limit around the standard rules and the max number of outputs possible, but that's still much better than 185 times worse. So to look at this in more understandable numbers in question of time, we can see here that the start produced this table just running the benchmarks on the examples that we have creating these big transactions. And the baseline for the different cases, we can look there, that is around 70 seconds for the 25K case. And then if we add the output randomization, we get an optimization by around half. So what I showed you before, something around that. And then if we add the batch inversion, we get a 4 times improvement. So adding these optimizations and limiting decay seems to be the best that we can get here.
Can you say how does randomizing the outputs help you? Just because your variance is less, how does that help your performance? performance time.
Yeah,
At best, it could be coincidental.
yeah, maybe that stabilizes the numbers in multiple runs, yeah, I agree that that's
Maybe batch inversion on its own without randomizing should be more or less the same, but I don't know.
Yeah, I should review this comic because I'm not sure that I agree with this. I was thinking here in the removal of outputs instead of the randomization. Maybe it's a typo, but I don't know.
Yeah.
But it's closer to what I said about the removal of outputs.
Yeah.
I have a question. It might be a little ignorant because I'm not like super fluent on how exactly silent payment works, but I know you have to tweak something.
Yeah.
Are you able to like, for example, you could do this when you're creating a silent payment enabled wallet. Are you able to pre-compute any of this and then use it later on?
Yeah, that's something that I have done in BDK. There is a project called BDKSP, that's an experimental like CLI tool. And the idea is that you are outsourcing the computation of the private information that you need to tweak your share secret.
Because I think it's fine if the UX of creating a silent payment wallet is you have to wait 20 seconds or whatever. You have to wait some time until the silent payment tweaks finish pre-computing, and then you can use it later on.
Yeah, but you still have to perform like
You still have to
in the case that I implemented, that was a combination of compact block filters with a server giving you the tweets. So I obtained the tweets, combined that with the keys from the wallet, and then produce a sketch to compare against the filter.
Okay.
And then we have to get the block and again run all these operations. But yeah, it's true that the pre-computing of the private information, this tweak, allows you to have some improvements. Well, and now I want to talk about the decisions based on what dimensionals were. So the idea was that the introduction of batch inversion was a good improvement for the worst case, and this idea of, well, we are also improving the scanning for people that doesn't have any side payment outputs in that transaction. And relying on limiting this, in limiting the number of silent payment outputs that you could derive from your transaction is also a good thing, because for the target attack, that's not something that we couldn't rationalize well. It keeps it bounded, and it removes a source of slow on the sky. So, and well, what goes next after all this? Well, we repeat. The idea now is that we have the stack has opened a PR trying introducing this change to the specification. We have already received some comments. So someone mentioned that users could be targeted at the same time by less money by sending using this limit and sending to different users. So it's like by around the number of users is by the same money you can spread your attack to like multiple users. And still, this case is limited for the single target use case, and at the end is the improvements that we got for the no matches user case stops us from having to worry about this case, because if we have multiple users that are attacked at the same time, let's say 2 users, one is going to compute the transactions that don't belong to him really fast. So at the end, it's not really a concern there. And another thing that that was mentioned in the review is this idea of keeping the number of derivations close to the standard rule, so there is no way to, by some heuristic, find silent payment transactions. So this process continues going on. So the idea here was to show you that there has been activity in the silent payment protocol. We continue working on this, and we continue iterating to make this case performant enough so we can have a great user experience in this code. So I want to thank all the reviewers and contributors that have engaged in this work, and it has been a really wonderful experience, learning experience for me to also have time to work on this. If you want any references here, I can show you later the presentation, but you can go to the PR Open libsecp, or you can go to the BIP PR that's open in the BIP repository, and all of the documents that have been created by this review process are linked in the different PR. So if you go to them, it's a good starting point to start learning more about silent payments. Questions? Yeah.
Statistically speaking, most of the cases are the cases that you're scanning a transaction but you're kind of not finding it.
Could you repeat that?
Statistically saying, most of the transactions that you're scanning are the ones that are not for you. So it kind of makes sense to, does it make sense to focus on the fact that, okay, I want to optimize my scanning for when you're not actually encountering it?
Yeah, that was the idea with batch inversion. So if you're improving the case where you are going through transactions that are not interesting for you, you should be scanning those very fast. And yeah, I don't think that there is, like, I'm not an expert in the cryptographic side, but the batch inversion was one of the greatest improvements. I don't know if there is any other else. So, okay.
Have you ever seen any type of attack to silent payments this time?
Well, we don't have any production implementations now, so it's very hard to say. I think that the only production implementation is the K wallet implementation, and I haven't received any mention to that from them.
I mean, so for example, like in core, this wouldn't impact block processing at all because that's separate. So then the wallet would need to scan after a block is appended and it gets that signal. Is like the main hiccup of bringing silent payments into core is that time, that potential time for scanning? Like, is that the main obstacle?
Yes, and the fact that the PR that should go in libsecp hasn't been met. So like we are in the phase where we are just optimizing the PR before going into libsecp. So I think that it is considered, but as part of optimizing the library instead of how this will impact in Bitcoin.
Yeah. Okay. No, because it wouldn't impact any. Because if you tell people, oh, it takes really long potentially to scan for these transactions, but like it should be clear, like this doesn't impact block validation. It impacts if you have a wallet that is opted in silent payments as a user of the wallet, and it doesn't impact your node and it doesn't impact miners. It's you using the wallet. It can potentially, for some time, take a really long time for your wallet to be usable again. Or not even usable, just to have its balance updated.
Yeah, that's true.
Because what I'm saying is some people might see the time and they might think, oh, no, we can't have silent payments because you're adding potentially 30 seconds or even 10 minutes to block validation, but it's not. It's just afterwards. And for you, if you have a wallet, and if you have a silent payments wallet, the scanning takes some time.
Yeah, I think that process can go separately. So you first validate the block, and then you get you start all your scanning process.
Yeah.
I'm not that familiar with how bitcoin works. But yeah, I don't have a clear answer for that. I don't know like if there is any like has there been any mention to that in the Bitcoin Core PRs. I know that it's someone working and always working on the receiver side, but
I mean, wouldn't it, if you...
He has not raised that concern in 70 library. Yeah.
Would it be problematic though if like you're still scanning and then some of these outputs that you're still scanning then get spent in the next block?
Like you would have to spend it.
Well, that's...
You would have to spend the output.
Sure.
Yeah, but you can't spend it until like you scan it.
Yours.
But then, like what I'm saying, but you do run into the thing where, okay, if it takes 10 minutes to scan, and a block arrived 8 minutes in, now you're still scanning, and now you have to scan another 10 minutes or 13 minutes, and then a new block comes in, and so you're like you're always scanning.
Yeah, I think that we don't actually we're interested in having something that is much less than a block propagation, the block creation time.
Yeah.
And well, I forget what the story. Yeah. Yeah, so GPU computing was mentioned, and someone has run some experiments there. Frigate implementation has run some experiments with GPU cores. The results have been like promising, but yeah, the thing is that we are still trying to find if we could slim down the case for a single for not parallel processing, but yeah, there have been really good numbers related to GPUs uses. Yeah. Actually,
I think you brought up a good point. If silent payments can be part of a multisig, can they be in a multisig?
Like the specification has left that open.
Yeah.
Because
but
if it's not specified.
Then scanning takes a long time, and that is a concern.
Well, I mean, you can also just be scanning addresses that aren't yours, and then those can still be spent by other people.
Oh, like a watch-only silent payment thing?
You're scanning, and then a block that's a transaction that's not yours, and then that transaction gets spent. Yeah. I mean, if anything, it just helps you. Like, okay, well now I don't have to worry about. I don't know. It might be complex to.
Related to that is an improvement that you can do. That is, if you find that the opus that you are about to scan has been already spent, you can skip those.
Yeah. Because, that's already in there?
No, it's not part of the cryptographic implementation. It's something that you can do as a policy. Yeah. Yeah.
Regarding the attacks, this is just so this implementation of discrete logarithm equality, this is just an assertion. It doesn't have anything to do. So you're not attacking the silent payment with it, or are you?
Good, realize.
Okay, the discrete logarithm equation, like equality check, this is doesn't have anything to do with attacking how you're creating the silent payment. No, it's just the fact that making sure that you're correctly computing the address. Or can you actually attack it if the check is not done?
What check?
The discrete logarithm equality.
That is?
The LEQ.
That's separate because like the LEQ is used for when you are trying to do a multi-party transaction, you want to ensure that the other parties are using the same keys that they are using for signing, and they are using the keys that they are using the right keys to write the silent payment output. So they cannot create your output with a different key and then like send that amount of Bitcoin to the body.
So it's just an assertion. It's not.
Yeah, it's an assertion. It's a verification process. So you can be sure that the silent payment output has been right, and the receiver is going to be able to scan that output. But yeah, that goes also with PSPT specifications. So it's like this is only focused on the BIP 352 BIP, that is the specification for salary payments, and then the other parts are like we are working on that, but like the first block that should go through is the cryptographic specification.
Like the desired outcome of the attacker is just to make it so that you realize you have money later. Like you're
I
just
think
trying to
so.
slow
Yeah,
down. That's the only real attack. It's just I'm just gonna slow down you from realizing you have money. It's not.
Yeah, we couldn't come up with something like worse than that.
Yeah.
Yeah, it's like just bothering. But if you're a government that is maybe printing money and has like spare money to spend, you want to censor the transaction from some particular person, and you will create enough of these transactions to like don't allow him to find their money. So it's like we are not so bad that we can come up with a use case for that. But
for like one thing you could do is you could make like a what are they like a rune or ordinals. It's like let's attack this one person, like mint like something to like here that is like a silent payment output for like this person, and you have like 500,000 transactions or whatever, like filling up all the blocks. So like you DOS someone.
Well-defined attack, just DOS someone.
But at the same time, you don't have to spend money on the receiver. Like if you collude with a miner, then it's much cheaper for you to make that attack. You don't have to send money. You don't have to comply with standard rules to create above dust. So it's like very easy for you to. So I wanted to show this image here. So that's the idea that someone that has a money printer can try to, like, it's going to be very cheap for them maybe to make this attack. So it's mainly slowing down the person doing the scan. That's the idea.
I guess your CPU is running hotter.
Yeah. Yeah, you are not getting you are not seeing the money that you are expecting.
All of this are for one address, so it scales with the address that you create for each person. It scales with the number of silent payment addresses.
If this scales with the number of different addresses that you are yeah, that's something that we were discussing in the latest iterations during the big proposal PR, and like. As the no match case is improved, maybe you're receiving like someone creates a transaction with 3 different receivers, 3 different select payment output addresses, and that transaction has like 3,000 outputs in total, sending 1,000 to each. But so one of the receivers, each receiver is going to have a performance degradation like what we have shown, but for the rest 2,000 outputs is going to be the batching version improvement that I showed, like 2 times, around 2 and 3 times faster. So it's not going to be that intensive for him.
Are we kicking off the hackathon over there? Yeah.
Okay.
We're on time.
No more questions? Oh, okay, thank you.